Hello, everyone. Welcome to another thrilling episode of Science Sunday. Yeah. This is a follow-on from, I guess, 3 weeks ago when I introduced the topic of special relativity. And I'm looking forward to today's talk. I just wanted to pile on a bit from this morning. People were talking about the virtues of this establishment and their membership, the DuPage Unitarian Universalist Church.
In the Sunday service that you
in the
watched
Sunday
there.
service, which is up on the YouTube channel. This establishment, this community of people has provided a welcome podium and a welcoming community to us to do Science Sunday for over 10 years. And, it really is delightful. I don't know where else in the world I could share my personal joy and love of understanding the natural world. And I don't know of many other churches or congregations in the world that would be so thrilled to have that kind of message. A lot of times people associate church with other explanations for how the world works and how it came into being. And there's a significant community here who are members of this church and who find it to be a happy home. Many of us love the scientific explanation.
And so today at the service, they were talking about evolution, which again is not a common topic in many denominations, but
Right.
it is an accepted and interesting thing here. And I thought a really good children's book was read today that was very clear and insightful and interesting and compelling. And all the times when you talk, there were Stephen Jay Gould quotes that were thrown out there too, which is kind of nice to see, and so on. So yeah, very, very nice, very rewarding to be a part of that community for me as well.
So if you're mostly tuned into these because you're interested in science, and if you live in the area of Naperville, Illinois, I recommend, if you have not yet, to check out this community when it's possible to do so, when we're congregating in person.
Which is coming up beginning of March 6th, 2 weeks from now.
Some
limited availability of seats and seating and so on. And so that's also my next Science Sunday coming up 2 weeks from now too.
So hopefully some people can show up in person for that.
Right.
Yeah. All right. So Science Sunday, relativity theory. A few years ago, I talked about relativity theory, but I crammed all of it into one lecture. This year, I'm spreading it out among 3. 2 lectures on special relativity, and then I believe in March, I'm going to talk about what's known as general relativity. And this is the second part of special relativity. You don't need to have seen the first part, hopefully, to get a lot of information from this one. One of the things that I hope to do today is that I hope to cover some topics, some implications of special relativity that you probably have never encountered, even if you've attended other science lectures about the topic. The implications of this theory are so deep and so subtle that whenever a presenter or an educator focuses on things like the twin paradox or time dilation or length contraction and things like that, it's so counterintuitive to explore those particular topics that sometimes the more subtle implications of relativity theory are not brought up to the
To the forefront.
To the forefront, yeah. I had an excellent email exchange with one of our viewers from last time. Eugene emailed me and wanted to know more about the twin paradox, and he was really doing a great job of just trying to think it through and figure out how it worked and maybe why it wouldn't work in certain contexts, and it led to a very rich exchange in email. I encourage all of you, whether you're watching this live or whether you're watching this as a recording, if you have a question or an idea, share it with us. If you're watching live, you can type it into the YouTube channel and ask a question or make a comment, and if you watch this later, you can leave a comment in YouTube. And you can always email Mike or somebody at the church, office at the church, etc. There are many ways to get a hold of us. We love talking about this stuff. That's why we've been doing it for over 10 years. So, again, this is your forum as well as it's not just a lecture. It's a place to learn and ask questions and grow. So I encourage you to take advantage of that.
One thing I just thought I'd ask you, that this whole concept of when you just look at the terms, the way they're set out, general relativity sounds like the basics, like lesson 1, and special relativity seems like this extra addendum or something thrown on the side, when really, I don't think that's really the case. The more I've looked into it, it seems almost as if, even in time frame, I think the special relativity by Einstein came out earlier. That's kind of the basic, the nuts and bolts of it. And then the general relativity are somewhat of the more, freelancing kind of off-the-wall things, which is counterintuitive in its own sense.
Yeah, so, oftentimes when we're exploring an aspect of nature, we will pick out a particular case study, whether it's a particular plant and we want to understand the physiology of a particular plant or tree. And that's a special case, right? You understand how nature works in a specific special context. And then you might later on think, well, I wonder if I can generalize this. Right? I wonder if I can draw conclusions and make statements about the way plants or genetics works in a more general way than just what's going on in this particular cell or this particular plant. Well, although it's not biology, Einstein did something similar. He was thinking about a very specific thing with the special theory of relativity. He was thinking about the implications of some 19th century discoveries about the way light works and the relationship between light and electricity and magnetism. And thinking through some of those implications, as we covered last week, he decided that it was logical and prudent to conclude that the speed of light remains constant for every observer, no matter how they're moving in what's called an inertial reference frame. That's a reference frame with no acceleration or no forces acting on it. So it's an object at rest or an object in constant motion. And Einstein said that the laws of nature, including the law that the speed of light has a particular value, all of those laws of nature, including the speed of light, have the same appearance, not necessarily. We talked about arc lengths of a falling cannonball and whatnot, how different observers could disagree about the total path length taken by a falling cannonball. Observers may not agree about certain aspects of nature, but they will all agree on the same laws of nature. And the speed of light is an implication of a law of nature. And
Does that imply that, let's say there's a speeding spaceship that's going
yes,
2/3 of the speed of light,
okay,
and right as it passes a planet, it sends out a beam of light. So both beams of light get turned on at the same time.
What's the second one? You just talked about one beam of light.
Well, the beam of light that's set out from a spaceship and then a stationary planet, let's say, that
sends
passes
out a beam
out,
of light. Okay.
and it sends out a beam of light at the same instant relative to each other, which again is another question too. But what would one light beam hit at different times, or?
Yeah, the idea of what time does something happen becomes more fluid in special relativity, because the notion of something happening simultaneously at a distant locale becomes open to interpretation. So, agreeing that something happened on a minuscule scale, of a few inches or maybe a few feet, nearly any observer in nearly any context will agree that events did or did not happen simultaneously on a short scale of distance. But if you extend your distance significantly enough that you can detect a phenomena and you speed past something happening like a lightning bolt striking two ends of a train, which I talked about last time, or actually was in a video last time, different observers moving at different relative rates will disagree about whether those lightning bolts hit the train front end and back end simultaneously, which is completely counterintuitive. That's one of the reasons that relativity theory is so difficult to wrap your head around. It's got a lot of absolutely counterintuitive notions, and the most fundamental counterintuitive notion is that time is malleable. Nobody is accustomed to thinking, unless you're a practicing physicist or a science aficionado who's spent a lot of time thinking about it, none of us is accustomed to thinking about time as being a malleable thing. It's the ticking of the clock, and we synchronize our clocks across the town, across the globe, across time zones, but that is the kind of activity that happens for people in a relatively common frame of observation here on our moving planet, where our trivial speeds of trains and automobiles and even jet planes don't really matter in the context of relativity. But to answer your first question, Mike, special relativity is about the special case of inertial observers. It's people in constant motion or at rest. A person in constant motion can just as easily presume that they're at rest, and the laws of nature will be indistinguishable. But if there's a force acting on you, like the force of gravity, then instead of objects remaining at rest in a force field associated with gravity, an object will just suddenly fall. So things change when you're in a more general framework that includes the effects of outside forces or stresses. And general relativity takes that more general view. Very specifically, special relativity is the application of this notion of a constant speed of light to this special case of space-time that is not warped or bent. And general relativity talks about warped or bent space-time as being an effect or the ultimate cause of what we call gravity. And I'll talk more about that next time. All right, well, let's begin. Let's jump right in with the hard stuff here. It's one of the life lessons that I have tried to integrate into my behavior is if you got something difficult, you try to start on it first. You leave the easier stuff for last, but if you're doing a project and you've got something really difficult to accomplish, go ahead and get started on that difficult thing first. Now, mathematics is perceived as difficult by a lot of people. And to be honest, it's not my forte. I never got a PhD in physics because one of the reasons is I'm not in love with mathematics, or at least I wasn't 30 years ago. So here's a little bit of mathematics for you. These are terms that are frequent in the study of relativity, especially special relativity. One is called the beta factor. It's just the ratio of your speed compared to the speed of light, or the speed of an object you're observing compared to the speed of light. So that's a beta factor. It's represented by the Greek letter beta, you see there. And then there's this this thing that has more implications in special relativity called the gamma factor. That thing that looks kind of like a Y is the Greek letter gamma. And it is 1 divided by the square root of 1 minus this beta factor squared. So it's 1 divided by the square root of 1 minus your velocity squared over the speed of light squared. And that gamma factor comes up again and again in special relativity. Notice that as a velocity approaches the speed of light, beta approaches 1, right? If you divide the speed of light by the speed of light, you end up with 1. However, gamma approaches 1 divided by 0 as your speed approaches the speed of light. Well, 1 divided by 0 tends to infinity. So the implications of these two mathematical factors can be quite profound when thinking about the way they apply to physical objects. Now, I'm not going to take the trouble today to derive these equations from the concept of a constant speed of light. But if you pick up nearly any textbook on special relativity, such as this phenomenal one by two of the greatest relativity scholars of the last century. It's called Space-Time Physics. It's by Edwin Taylor and John Archibald Wheeler. This does a phenomenal job of explaining the algebraic details of how we come up with these equations and then how to apply them. I believe this book is freely available as a PDF online, in fact, but you can certainly try to find a physical copy as well. But I'm not going to go through the grueling mathematical derivation. Some of you may find it grueling. It's mostly just algebra, so it's not that bad. But I will ask you to notice something interesting. By the time you expect the effects of relativity to become significant, let's say 1.5, you expect a clock to slow down by a factor of 1/2, or 1.5 times your duration, or you expect a length to be contracted by 50%. In order for that to occur in the context of relativity, you must be going at 78% the speed of light. Not 50% the speed of light, or twice the speed of light, which you can't do. But in order for this 50% effect to be relevant, you have to be going at 78% the speed of light. And that's because of this weird square root formula for the gamma factor that I showed you earlier. This is a plot of the value of the gamma factor compared to your percentage motion through space as a percent of the speed of light. So on the bottom there you see essentially percent light speed or fraction of light speed. 0.1 is 10% light speed, 0.2 is 2% light speed, 20% light speed, etc. So this gives you an idea of why some of the most profound and bizarre effects of relativity, special relativity, don't happen until you're moving at nearly 90% the speed of light or greater. And then it's what's called a hockey stick or a hyperbolic curve. So that's why particle accelerators, for example, try to get electrons or protons to move at 19.99999 times the speed of light, 99.9999% the speed of light, is because some of the more profound aspects where you can really pump strange behaviors out of relativity don't happen until you're going at speeds like that. All right, this is another page of math. This is how to use those gamma factors in questions that you can play around with in the comfort of your own home. If you want to program this into an Excel spreadsheet or a computer some other way, you can find out the rate at which time slows down if you're looking at a moving observer, as it's just your rate times the gamma factor. And then that's your rate, which is represented by dt, divided by 1 minus beta squared. So it's just a little bit of math to figure out how clocks vary, how length contracts. And those are things we talked about last time. Pretty straightforward algebra. If you have a kid in high school, they can probably show you how to do this. Next is the relative energy of an object in motion. I thought a long time when preparing today's talk, if I wanted to go into this in detail, to go through the mathematical derivation of E equals mc squared. And I decided not to because it would take probably half the lecture just to go through the math and the algebra. But again, I recommend you can look up articles online, you can look up all kinds of resources online that will go through the derivation of this. Brian Greene has an 11-hour presentation online about the special theory of relativity, and he goes through this. So I'm not going to do this today. I'm just going to state it as a fait accompli, and I hope that that doesn't disappoint anyone. But you can find this derivation.
And Green's derivation, Green's lecture is fascinating.
Yeah.
I mean, you can start at the beginning and go for quite a ways, and you understand quite a bit of it. He really has it well ordered in a way that makes you comfortable learning this stuff.
He does a great job, I think. So relativistic energy comes from the conservation of something called momenergy. It's a word that was made up just for relativity. It's a combination of momentum and energy, both of which are conserved in our universe. And when you combine them and recognize that there's a trade-off between momentum and energy, just like there's a trade-off between motion through space and progress through time in relativity. When you combine those concepts together, you come up with this notion that an object in motion has a total energy of mc squared times the gamma factor. And using something that you learn in the first year of calculus studies, you can break apart that mc squared over the square root of 1 minus beta squared. You can break that apart into smaller bits and as an infinite series. And the first two terms of that infinite series say that the total energy of a moving body is equal to 1/2 mv squared plus mc squared, plus some other stuff that depends on like 1 over v to the fourth and whatnot, that becomes such a trivial contribution that you can ignore it typically. But anyway, 1/2 mv squared, well, that's kinetic energy. We learn about that probably in high school physics and certainly in college physics. So the total energy of a system is 1/2 mv squared plus mc squared for speeds much less than the speed of light. And we're familiar with the implications of turning mass into energy. Probably the most disturbing one is the notion of atomic weapons, which release some of the energy pent up in the nucleus of an atom, or a couple kilograms of atoms. It releases those as a burst of heat and light. And the shock wave in our atmosphere caused by all this heat and light causes a pressure wave that can be incredibly destructive. So atomic weapons work because in the nucleus of an atom there is stored energy. And we'll talk more about the details of that in just a minute. We can release that energy in a more controlled manner for nuclear power. It allows us to get energy out of rocks on Earth, certain rocks that contain certain radioactive elements. Now here's something you may not have thought of. Every time you exercise, you're actually turning mass into energy. Now, not in an appreciable way. You're not going to burn a kilogram of energy by running for a marathon. But the energy of the chemical bonds in the food you eat are broken apart and that energy is released. And it's that energy release that drives tiny little molecular machines, little proton pumps in the mitochondria of your cells. And through the Krebs cycle and other things you've heard about in biology, the breaking of these chemical bonds and the creation of new chemical bonds has the net effect of liberating a little bit of chemical energy. And it's that chemical energy that propels you every time you move through space. But if you were to have a balance scale that could measure 1 quadrillionth of the amount of weight in a carbohydrate molecule, you'd find that the carbohydrate, before it is oxidized, weighs a little more than after it is oxidized, if you collect all the parts. And a tiny bit of mass has been converted into energy by the oxidation process. So we are all powered by E equals mc squared. Every chemical reaction that is exothermic liberates a little bit of energy. Every chemical reaction that is endothermic, that requires energy in order to form new bonds, is consuming energy. And energy in these cases transforms in the way that the mass of the reactants is implicated in the interaction or the chemical reaction. So E equals mc squared is relevant to chemistry, but no chemist typically bothers with mc squared because the c squared part is a gigantic number compared to the amount of mass involved. So it's just not worth it to calculate energy from E equals mc squared. Instead of they assign other energies like heat of enthalpy and the kilojoules per kilogram of a particular reaction and whatnot. But at a fundamental level, all of that happens because of E equals mc squared. Huh. Batteries. A charged battery weighs a little more than an uncharged battery. Now, don't go home and get out your kitchen scale and try to figure this out, because the amount of mass change, even in a high-capacity modern battery, is so trivial that you won't be able to measure it with any device that you have ready access to. But it does happen. A charged battery with more energy stored in it weighs a little bit more than a drained battery where that energy has been liberated. A tiny fraction of mass has been converted into energy.
It recalls to me the experiments that they tried to do, or the investigations that they tried to do as people were dying in hospitals, and they put them on very, very calibrated beds that were basically large scales, and they were looking to see if the soul
Had
any energy, had any weight to it or whatever.
Yeah.
And never really found anything like that.
Yeah, unfortunately, I mean, there's all kinds of ways to use science to investigate extraordinary claims. But so far, there's not been any definitive evidence or persuasive evidence of a violation of the laws of nature, including the conservation of what is now called mass energy. You probably learned in school about the conservation of energy. The more broadly applicable and more generally correct statement is that there's a conservation of mass energy in the universe, because energy can be stored as additional mass. And I'll give you some examples of that in a minute. So here's a graphical representation of a hydrogen atom. The electron is circling a proton, and when an incoming photon, the purple photon, hits it, it can jump up to a higher energy level. And then the electron decays into a lower orbital that releases that same sort of photon. Well, here's the interesting thing. Where does that energy go? If energy is conserved, where does it go? Well, it goes into the orbital motion of the electron, but even more profoundly than that, a hydrogen atom that has an excited electron, an electron in a higher energy state, weighs more than an electron in a lower energy state. But if you really think that through, that means that if you have an electron on a scale and a proton on a scale, if you bring them together, the sum of the mass of the electron and proton is actually greater when they're apart than when they're together. A hydrogen atom weighs slightly less than a proton and an electron combined by themselves. Because as the electron plummets in to orbit your single proton, it releases energy. It releases potential energy. It settles into a lower energy state, comfortably orbiting the proton of a hydrogen atom, and in doing so, it liberates some energy. That means that if you measure the mass of an electron and measure the mass of a proton, and then bring them close enough that they slap together into a hydrogen atom, that hydrogen atom will weigh less, slightly less, than the separate parts weighed to begin with. That's E equals mc squared.
They're essentially studying that as they bombard protons in CERN or over here at Fermilab when they did it.
I'll get that.
They're looking, okay.
Yeah, I'll get into that in just a second. So here's a graphical representation of the ways that the distribution of probability of finding an electron changes as an electron climbs up through the orbitals of a hydrogen atom. These are the computer-calculated probability diagrams of where the electron resides in different energy levels. So I don't want to mislead people to think that the Bohr model of the atom of a little solar system with a proton and an electron spinning around in a neat little orbit, that's not the way it seems that nature works. Nature is far more complicated on the microscopic scale, and you need quantum mechanics to figure it out. So I just don't want to mislead anyone, but for the purposes of educating about the way an atom works, the diagram there on the left is useful for pedagogical reasons. So every time you eat food, you're taking in carbohydrates and other sugars and proteins and whatnot that are liberated through metabolic processes. And in the process, that means that the waste material that comes out of your digestive system weighs a tiny fraction less than the food that you consumed because you've extracted energy from that food. And that's the way every living thing on Earth maintains that mass energy conservation. All right, nuclear binding energy. Mike, this goes into something you were talking about. An electron volt is the amount of energy gained by an electron as it accelerates through 1 volt of potential. It's just a useful measure that particle physicists use. In an atomic nucleus, for non-radioactive elements, generally you've got about 5 megavolts of energy stored. It's just another way for measuring energy instead of kilowatt hours, etc. About 5 megavolts of energy per nucleon that goes into assembling an atom. The mass of a proton or a neutron, they're about the same, is in these units 1 gigavolt. So 5 megavolts compared to 1 gigavolt of energy is released whenever a nucleon is added to a nucleus, whenever you add a proton or neutron. Again, up to a particular level. And I'll talk about that level next. Elements lighter than iron 56 or nickel 56, 56 is the count of the sum total of the neutrons and protons in their nuclei. Any elements lighter than this iron or this nickel release energy when they bind together. This nearly 5 megavolts per nucleon. So if you were to bring a neutron or a proton from outside and somehow put it into the nucleus of a carbon atom or a hydrogen atom or a silicon atom or any element lighter than iron, with a lighter nucleus than iron, you will actually liberate energy. That's how we get nuclear fusion energy. You've heard of fusion bombs and putative fusion reactors that might be a source of limitless clean power. That's because whenever you are able to smush nucleons together in anything lighter than iron, you get out a little more energy than it took to bring them together in the first place. But there are some complications to that. You're trying to shove a charged particle like a proton into a nucleus which also has a charge. And the electric charge works against you, literally does work against your force to try and get another nucleon into the nucleus. And those particles have to get close enough that the strong nuclear force that only has a very short range, about the size of a nucleus, can grab onto that nucleon and say, "Ah, you're mine!" Kind of like a proton grabs onto an electron in a neutral hydrogen atom. The problem is electromagnetic forces have an infinite range, but the strong nuclear force which binds together a nucleus has a short range. So you have to put some energy in to overcome the electrostatic repulsion before you get fusion happening. So how do you get...
Did you say electrostatic repulsion, right?
Right.
I didn't hear if you said repulsion or propulsion, but repulse.
Yeah, repulsion.
Yeah.
You know, nuclear fusion is what powers the stars, and the way they give their particles enough force to overcome electrostatic repulsion is by having a crushing force of gravity. Now, when we try to do that on Earth, we do it a little differently. We bring a hydrogen atom which has an extra proton, so you can put a proton and a neutron together, and it makes something called deuterium. And then you can take a proton and 2 neutrons, making something called tritium. These are both variations on the theme of hydrogen. And if you bring them closely together, then the extra neutrons involved in this reaction will provide a little more nuclear glue and facilitate a little lower threshold of activation energy for them to bind together as a helium. So this is the kind of thing that is done in the fusion reactors on Earth, is that they try to allow the nuclear energy of about 5 megavolts per nucleon in a given nucleus to be liberated by smushing them together with ideally less than 5 megavolts per nucleon of energy put into the system to accelerate them into each other in the first place. So nuclear power is a way that E equals mc squared is able to be taken advantage of. Now, here's a really cool thing. This is a picture that scientists have developed by running some of their models of reality on a supercomputer. This is a model of what they think the interactions between the quarks inside of a proton or a neutron look like. And it's just incredible jumble. And one of the reasons for that is because the glue particle that holds quarks together is charged also. It's a special kind of charge called a color charge. But the end result is you just have this absolutely sloppy mess of quarks and gluons or glue particles inside of every nucleon. And in fact, 99% of the mass of a proton or a neutron is bound up in the energy of this interaction. If you were just to somehow be able to separate out, and I'm not going to go too far into particle physics today, but if you could somehow separate out the quarks that make up a proton and a neutron and added up their masses, it would be trivial amount of mass compared to the mass of a proton or neutron, because much of the mass of a proton or neutron is composed of the energy of interaction and motion between the little things that go inside of it. So potential energy, energy of motion of an electron orbiting an atom, energy of motion of any sort in a closed system, that energy contributes to the total mass of the system. And if you have a tremendous amount of motion and a tremendous amount of interaction, then it can make up the most appreciable percentage of the mass. This is an implication of E equals mc squared. Here's another implication. Now, instead of atoms, we're going to talk about colliding black holes or neutron stars. When astrophysical objects coalesce, they weigh less than they did when they were separate. So where does that energy go? Well, it can go into a flash of light, and it can also go into gravity waves. In fact, when black holes coalesce, when they start spinning furiously around the common center and then merge into a single object, the leftover black hole that results from that merger must necessarily weigh less than the two black holes that it began as. And where does all that energy go? Most of it is emitted as gravity waves. Several suns worth of energy is liberated as gravity waves when astrophysical black holes merge. Again, an implication of E equals mc squared. The total gravitational energy, that's represented by U in this equation, again, some simple algebra. The total gravitational energy locked up in an object is 3 times Newton's gravitational constant, that's the big G, times the mass squared, divided by 5 times the radius of the object, assuming it has a constant density throughout. But my point is that using just simple algebra, you can explore some of these phenomena on your own to figure out what is the gravitational binding energy of the Earth or the Sun or Jupiter. Again, you presume that the density remains constant. If you don't presume that, you can turn this into a little bit of calculus and solve it. But binding energy is often negative. It subtracts from the total energy of a system. So, what does that mean? That means that in things heavier than iron, for example, you have to put in more energy than you would liberate by separating them. And if you consider the whole context of the universe as a whole, the energy stored in the gravitational potential of all the scattered bits of galaxies and quasars and black holes and everything else in the universe, think about the potential energy locked up in that compared to the energy that would be liberated if it all came together and smushed into a giant black hole. There are speculations that it may be the case, there's no definitive answer on this yet, but it may be the case that the total net energy of the universe is 0 because of that, because the gravitational binding energy contributes to the negative side of the total energy balance of the universe. And this is something that's talked about in more detail in A Universe from Nothing, a book by Lawrence Krauss, if you're interested in learning more about that.
I haven't heard from him much lately. Has he been staying with that same concept?
He has a podcast and a YouTube broadcast, but he got into some hot water because of sexual assault allegations that the University of Arizona, investigated and found plausible. So his public status has diminished a bit. So in a particle accelerator, what happens? Well, in a particle accelerator, the huge amount of momentum and energy locked up in a quickly moving particle can be translated via E equals mc squared into other particles. So here's an example from something called a Wilson cloud chamber, one of the earliest detectors of the debris and detritus emerging from a particle collision. And these have evolved in the past 60 or 80 years to the point where things like CERN and Fermilab use electronic detectors.
So is this almost like a negative, like it burned an image on a screen or something, or is that a representation, or?
That's a photograph of something called a bubble chamber.
Yeah.
So charged particles, when they move through supersaturated gas, supersaturated with a liquid, a potential liquid. When a charged particle moves like that, they'll leave a condensate trail behind them, kind of like a contrail from a jet. Mm-hmm. And so these are the contrails left by charged particles, and it's literally just a photograph taken through a transparent window into the cloud chamber. So here's an example of a typical collision that happened at Fermilab, and something similar to this happens at CERN. I think CERN uses 2 proton beams instead of a proton and an antiproton, but the details in that regard don't really matter. Here you see a proton coming in and another proton coming in, or an antiproton, and they smush together and they make a cloud of debris. And interestingly enough, if you were to recall that a proton, as well as its antiproton equivalent, they both have a total mass energy of 1 gigavolt. But if you smush them together violently enough, they can emit particle debris such that the particles emitted weigh vastly more than just 1 gigavolt. 1 gigavolt. Well, how does that happen? Well, the energy of motion is translated into energy of mass of the resultant particles, which move much more slowly than the initial protons, which moved at 99.999999% the speed of light, or thereabouts. Now here's another incredible thing you may not hear in other lectures about relativity. Magnetic forces. So if I have a stationary proton sitting next to a wire with a current flowing through it, that proton won't move, because the charges inside the wire distribute themselves in such a way that the wire remains electrically neutral, even though it's carrying a current. So if it's electrically neutral, there's no electric force on a stationary proton sitting outside the wire. But now, if we were to put that proton into motion, suddenly there would be a force on it, a force pressing it upward. And if you combine the motion of the force directing it upward and its already present forward velocity, you get a curved trajectory moving away from the wire. Now, as an interesting side factoid, electrons in a current-carrying wire do not move at the speed of light, nor do they move at the speed of sound that the wire might allow. In fact, the electrons in a conductive wire move at about 1/3 of a millimeter per second. That's just an interesting factoid. They're not moving, the point is they're not moving anything like close to the speed of light. So in any case, when you have a test particle, like a proton, moving near a wire that's carrying a current, it will experience what we call a magnetic force. But Einstein said that motion is relative. So what if I move along with that proton? Well, will I see the proton move or not? If I don't, then suddenly the laws of nature disagree between my moving reference frame and the reference frame of somebody in a laboratory watching all of this excitement happen. Why is that? Well, here's where special relativity comes in. If you're moving along in the reference frame of a proton, then the wire seems to be zooming out from under you. And in that case, because the wire has a tiny velocity, doesn't have to be very big, there's a tiny bit of length contraction appropriate to the distances between the protons and the crystal and lattice of the metal making up the wire. If you were to count carefully between the upper two pictures and the lower picture, you would notice that I snuck in one additional proton in that same length of wire. That's because the charge density of protons in the wire, from the perspective of you moving along with this charge test particle proton, the protons in the wire bunch up a little bit. Not much, but just a little bit because of their tiny motion relative to you. And that tiny motion and the incredibly minuscule contributions of Lorentz length contraction, or relativistic length contraction, cumulatively across billions of atoms of copper or some other conductive metal, the cumulative effect of those tiny, tiny adjustments due to special relativity mean that you see a greater force, an electric force. There's an excess of positive charges in the wire. And that excess positive charge causes you to move upward away from the wire. So in your frame of reference, moving along with a proton zooming over the top of a current carrying wire, you will notice that there's an upward force. Now, you won't have a curved path.
You won't notice a curve.
You won't notice a curved path, but you will see the same force contributed. So what does this mean? This means that in the laboratory frame of reference, what we interpret as a magnetic force due to a current, in the context of the moving particle, it's an electric force due to motion. So an electric and a magnetic field can be interchanged in certain circumstances by turning one into the other with nothing but motion. So that just like there's a relationship between space and time in special relativity, there's a relationship between magnetism and electricity. And that relationship was already explicated by James Clerk Maxwell 30 years before before Einstein came up with special relativity.
Is that an electrical repulsive force because there's a greater density in relation relative to the proton, and it's having more repulsive forces going by it?
Yes.
And so it moves away?
You are absolutely correct.
Wow. You know, just a little aside maybe, because this is challenging stuff. When I ride my bicycle pretty regularly, or whenever I ride my bicycle, I have a habit of counting the number of cars that are passing me each way. So, you know, it's no great, it maybe helps to perceive this better, but obviously, as you go, you see a lot more cars passing you.
Per unit time.
Right.
Yeah.
In the same distance or same time, passing you from going towards you, then are passing you from behind. And you say, oh, lucky me, today I'm riding with traffic. I'm riding in a more pleasant way because not as many cars are passing me in the more dangerous situation of coming from behind.
Right.
But it's really the fact that I'm moving along at some rate.
Relative to traffic, yeah.
Yeah, so that less cars can pass me up in that same distance, whereas more cars can come towards me in that same distance.
It has to do with your point of view.
Right.
Yeah, exactly. I mean, what you're talking about is an implication of Galilean relativity, but Einstein's relativity would have us understand that the distance between the cars actually changes as you move. Minusculely, at the speed of a bicycle or of an electron flowing through a wire with current, but considering how tiny a proton is and how many trillions of protons are compressed into a noticeable length of wire. The cumulative effect of those minuscule adjustments to the distance between the protons means that there's a positive charge density that you perceive in the wire. And it's the charge, the electric charge, that pushes you away from the wire in that context instead of what we would call a magnetic field.
But were you talking about the speed of the copper protons that are inside the wire? I always thought that they don't really move, but they're just vibrating, or so much energy in them that the conductivity passes from number 1 to number
Yes.
2 to number 3 to number 4.
Yes.
And that's the speed that you're talking about, and it.
Kind of. It's not the protons that convey the
Yeah.
electric, the change in the electric field that constitutes the current. It's the fact that the electrons are more mobile. From your perspective, the protons remain fairly fixed. It's a fixed lattice.
Right.
But if a lattice of charged particles moves past you, the distance between each lattice point is foreshortened. And that means you can squeeze more of them in to a given volume. Meanwhile, the electrons are so mobile in a wire that they can easily compensate and make the total charge from the perspective in number 2, where it's the moving electrons that create a magnetic field. Because electrons are more mobile within the lattice of a wire, the crystalline lattice of the atoms that constitute the wire, they can arrange themselves to get rid of any net charge. But a proton locked in a crystal lattice cannot rearrange its position. So if you're moving past it and you see this density increase in those charges, that's what gives you the net positive electric charge that repels you. Yeah, the 1/3 of millimeter a second is called the drift velocity. That's the drift. That's the average velocity that between all of its jumbled up movements through a wire, there's a little net drift in the direction of the current for a given electron, and it's really small. So magnetic forces are simply electric forces in another frame of reference. Now, there are certain contexts in which you cannot create a frame of reference that makes all magnetic forces disappear, but in this particular example, you can. Now, I want to talk about a couple of interesting elements on the periodic table. Gold and mercury. Gold is beautiful, it's ductile, it's chemically inert, it's what's called a noble metal, like a noble gas, doesn't interact well. It's because the atom of gold is so large that its outermost electrons orbiting the nucleus of a gold atom, those electrons achieve relativistic speeds. And because they achieve relativistic speeds, it effectively increases their mass. Well, that means as their mass increases, they fall in closer to the nucleus of the atom. So the outermost electrons available in nearly any metal, available for conductivity and whatnot, are buried a little inside the atom of gold. Nearly every metal is opaque to ultraviolet light. It absorbs ultraviolet light and reflects visible light. That's why we see metals as shiny and silvery, including silver. But in a gold atom, because that electron has migrated in toward the nucleus a little bit, it's not as readily available to interact with photons of visible light. So gold absorbs, instead of ultraviolet light, it absorbs blue light. And the colors that are reflected back, that are left over, that aren't blue, make gold. And that's because of relativistic effects on the atoms constituting an atom of gold. It also tends to hide the outer electron in the metal in a way that makes the metal not able to interact with other atoms. So it's one of the reasons why gold is an inert element, a noble metal. Now, you can do this easily on a calculator. This is the simplest equation in the whole talk. If you want to know what percent the speed of light the outer electrons in an atom are going, divide the number of protons by 137, and it's that fraction of the speed of light. So if you do that for gold, which I forget the number, 81, 79, something like that. If you divide the number of protons in gold by 137, you come up with something like 58%. So those outermost electrons are moving at 58%. Well, mercury is right next to gold. It's the next heaviest atom. Why isn't it gold colored? Why does it behave differently? Well, gold still has enough reactivity left to bind. Remember, it's got one available extra electron, and that one electron really wants to party with others. So gold has enough reactivity to bind to other gold atoms, and it makes a solid. Whereas at room temperature, mercury, with one additional electron in its outer shell that is also buried in towards the nucleus because of a relativistic effect, well, those electrons are happy together. 2 electrons in a orbital, suborbital, gets into chemistry that we don't need to talk about. But the net result is that mercury doesn't bind to itself as strongly as gold atoms binds to themselves. So mercury is a liquid. Because of relativity. Isn't that cool? When you look at the Bohr atom, incorrect but pedagogically useful diagrams of gold and mercury, you'll see that gold has 1 extra electron in its outer shell, moving at nearly the speed of light. But mercury has 2 electrons in its outer shell, moving at nearly the speed of light. And the difference between 1 electron being available and 2 electrons being available makes all the difference in some of the physical and chemical properties of these 2 elements. Here's another thing. Relativistic electrons in a magnetic field, or any electron in a magnetic field, will tend to spiral around what we call the field lines. And as they spiral, light is emitted perpendicular to the acceleration of a charged particle. So little beams of light come off of there. Here's an electron spiraling, and as it spirals, it emits an electric and a magnetic wave, electromagnetism. Now, if this happens to an electron moving at nearly the speed of light, the light it emits is squished into a cone of light pointing in the direction of motion. Again, this gamma factor tells you how squishy it is, how much it's squished. So what does this mean? If you get a moving electron accelerating around a magnetic field line, the beams of light emitted by that accelerating particle are rotated around into the forward direction. So in the rest frame of this accelerating electron, it's emitting light in all directions. But if you look at it from a stationary or more stationary standpoint, you'll see the light of an electron emitted in a cone pointing forward. We can see this evidence of this real relativistic effect from an object the size of a galaxy. This is a galaxy called M87. It's got a jet of material pointed nearly at the Earth, and we see it. But it just so happens that in such objects, basic physics dictates that there's a jet in the other direction, but we don't see that one. That's because the light from that distant jet on the other side of the object has its light beamed away from us, so we literally don't see it, but it's there. There are some contexts where we can see both beams. This is not a galaxy, this is a star that has a similar phenomena. But the electrons and protons constituting the jet of material in this beam are not moving nearly as quickly as the electrons and protons and ions emitted from the galaxy. So we can see both jets. And here's an example of another galaxy where it's actually the jet on top is pointed slightly at us, and you see the little white bit near the center? That means that it's much more intense radio waves in our direction compared in the direction away from us. This is called relativistic beaming, and astronomers who study jets around galaxies or quasars or protostars, etc., have to take this into account. Deep insights. Am I able to go like 10 or 15 minutes over today? Is there a problem with that? There's nothing else scheduled? Okay.
Right.
All right. So deep insights, part 1. There'll be 3 of these. Part one, here's a diagram showing simple motion in one direction through space. That would be the X green axis there on the bottom. You can either move forward or backward through space according to this diagram. And it's also got, in the same units of measure, motion through time. So to turn time into distance, you multiply it by the speed of light, or a velocity. So meters per second times seconds gives you meters. So the scale of both of these axes is in meters. But the conversion factor between motion through space and motion through time is huge. It's the speed of light. 299,000 meters per second. So here is a pedestrian object. Hopefully the pedestrian doesn't hit it with their foot. This is a rock laying on the ground. And here's how the rock moves through space-time. You ready? This is exciting. This is a rock moving through space-time. It moves only through time and not at all through space, neglecting things like, earthquakes and wind gusts, etc.
So it's just a stable rock laying on the ground.
Right, it moves through time. If you're sitting stationary in a chair, in the context of the inertial frame of the Earth, you're moving through time, but not through space. Now, if instead, by the way, this is the motion. The total motion of this rock is represented as motion through time and nothing else. Now, here's a rocket ship. This rocket ship is better than any rocket ship humanity has ever built and possibly ever will build. But this rocket ship moves at speeds close to the speed of light. And what happens? Well, if you look at the trajectory of this, the red line means that it's moved that far through space, but it's hardly moved through time at all. So this is the implication of special relativity. But it gets even deeper than this and more wonderful. The near light speed spaceship moves mostly through space and hardly through time. I already mentioned that. It gets more wonderful than that. As you're sitting still, you're moving through time with a certain rapidity. That's the technical term from the science of special relativity. You're moving through time with this particular rapidity. If you walk to the refrigerator, you're now moving through space, and you give up a tiny amount of movement through time for a movement through space. And in this context, every object, everywhere, every when in the universe is moving through space-time at the speed of light. You're either moving at the speed of light through time, or you're moving less than the speed of light, but you're giving up some of that motion through time to move through space. It's always a trade-off, even at a pedestrian velocity. Now, the amount of motion through time you give up in a Formula One car or a jet is tiny because it's a tiny speed you're going at relative to the speed of light. But it really happens. They've put clocks up on jet planes, and they've measured that a moving clock moves more slowly, even at a jet speed, than a stationary clock. This is a real effect with real measurable predictions. And that's why Einstein's insight tells us so much more about nature than we would have known otherwise. Everything in the universe always progresses through space-time at the speed of light. The speed of light is a conversion factor between motion through space and passing through time. Combined progress through space-time is a constant for all entities. Photons and gravitons, which have no mass, only move through space and not at all through time. That's the reason light moves at the speed of light, and so does gravity move at the speed of light. The carriers of the force, not to put too fine a point on it, the carriers of the electromagnetic force and the gravitational force have no inherent mass, so they inherently move at the speed of light, but only through space, and they don't move through time at all. This is a profound insight, and a beautiful one, I think. Well, here's another implication of the theory of special relativity. Back in the early 1900s, People like Erwin Schrödinger and Dirac came up with quantum mechanics. Heisenberg and Einstein and Born and Bohr and so many other people were involved as well. But you may have seen, at least pictorially represented somewhere in your life, the Schrödinger equation. Or you may have seen something called a Feynman diagram. He came along later in the 1950s and 60s and helped elucidate the way that quantum mechanical interactions occur, facilitated by limitations due to the constant speed of light. Well, here's a version of the Schrödinger equation. Now, this is for illustrative purposes only. Don't worry about the math in any kind of detail if this is something you find intimidating. What you can notice is that these things are constants. H bar, 2 pi, the letter I representing the square root of -1. These are all constants. So if you take out the constants and you focus on these bits, these indicate a change in what's called the quantum wave function. Again, not enough time to go into that today, but these are the change in the first one on the left is the change in the quantum wave function over time is related to the negative rate of change of the rate of change. That's why you've got that squared symbol there. It's the rate of change of the rate of change of the wave function in space. So the rate of change of the quantum wave function in time is related to the rate of change of the rate of change of the wave function in space, plus some other stuff that has to do with any potential electric fields or other potentials available operating on the wave function. But Paul Dirac and others looked at this equation and they thought about relativity. Well, relativity treats time and space on relatively equal footing. But this equation doesn't treat time and space equally. So what Dirac did was he came up with a version. If you look at the far right-hand side of this equation, it's got the change in the wave function with respect to space and time over time. So Dirac was able to come up with a quantum wave function description that included the equal footing idea of relativity. And when he did that, he had to put an mc squared. There's another thing from relativity that sneaks into the equation. So thinking about the implications of special relativity at the quantum world level gave rise to a whole new view of the way quantum and particle physics works. And one of the predictions that came out of this or related equation was the existence of antiparticles. Again, an implication of special relativity. Interesting stuff. You can solve this wave equation. There are types of equations in mathematics and physics whose solution is not a number, but their solution is another equation. It's kind of a meta thing. And this is a solution for the Schrödinger equation. We're going to talk about this one for just a second. So this is something called a wave equation. This describes the wave function through space and time. And this blue and red lines indicate one representation of the wave function. You'll notice that they're offset. Well, they describe the same phenomena, but you can easily pick an arbitrary offset, and they will still describe the same quantum phenomena. Because a wave and a circle and a triangle, these are all, if you remember trigonometry, they're all intimately related. And if a wave has to do with the motion of a particle through space or in an orbit, it doesn't matter where in the orbit you start looking at the particle, the wavelength and the wave amplitude and et cetera will all be the same. But you can start at any point you want. The phase of the wave is arbitrarily chosen. You can have a complicated wave because of many interacting things. This could be another sort of solution of the Schrödinger or Dirac equations with a complicated wave. But one of the other implications of relativity theory is that all interactions are local, whether you're hitting a baseball or falling off of a bicycle, which I know you've done a couple times. All interactions are local. Even the force of gravity, the mass responds to the local properties of space-time. We'll get into that next time I give a lecture. All interactions are local. Well, what does this mean? If you think again about that equation. This is the equation plotted out in time, a wave equation. And you'll notice there's that little jump about near the number 3. I programmed this, and all I did to make that little jump was I changed the phase of the wave at that juncture. I just changed its phase by a little bit. Well, when I change the phase, suddenly the whole profile of the wave changes. Does that say that my whole physical system is now changed? Well, a couple of brilliant physicists back in the 1950s, C.N. Yang and Robert Mills, were also bothered by this idea that the initial phase can be arbitrary, but if you decide to change it, because all changes happen locally, in order to preserve the state of the quantum system, you'd have to change the whole wave function everywhere in the universe all at once just by making an arbitrary choice for where the phase started initially. And this is related to something called gauge theory, which says you can move a gauge at any point along a measurement, and it's going to measure the same net effect. So what they did was they came up with a cheat term. They added into the equation for a quantum system. And they made this cheat term such that it will completely cancel out the sudden jump in that profile of the wave function due to an arbitrary change in the phase. And they found something amazing. This is a quote from a book. If the phase of the wave function changes, the function of AX, which they introduced, whatever it may be, must change in such a way as to exactly cancel out the problems introduced by that derivative, that change in time or change in space operator. And when they figured out, just arbitrarily introducing this cheat term to make sure that all interactions remain local, and you couldn't change that wave function's shape everywhere in space all at once, when they figured out the details of what that equation is telling them, it turns out it was the photon. They had described a brand new way of characterizing a photon in response to an accelerating particle. So the photon exists because there's a finite speed of light in our universe at a very deep level. And again, I'm running out of time. I don't have time to explain that in more detail. The photon must exist because of special relativity. And then this is the final thing. Emmy Noether, who was a contemporary of Einstein's and largely overlooked, never got a Nobel Prize, she made one of the most profound insights in all of the history of physics. That anytime you have a continuous symmetry, there must be a conserved quantity. So there's a symmetry. I can do an experiment today, or I can do it yesterday, or tomorrow, or 1 trillion years from now, and the results of the experiment will remain the same. There's a symmetry associated with when in time I do an experiment. Similarly, there's a symmetry associated with where in space I do an experiment, assuming that there's no external forces and whatnot. These symmetries are associated with a conserved quantity. Symmetry in time is associated with conservation of energy, and symmetry in space is associated with the conservation of momentum. But remember that diagram with that sweeping arm I wrote that shows a symmetry between moving through space and moving through time? That's a new kind of symmetry, and there's implications of that for a conserved quantity. And the implication is that there must be a thing in the universe that's conserved, and we call that electric charge. It's because of the constant symmetry between motion through space and motion through time. The direct, deep implication of that is that electric charge must exist as a conserved quantity in the universe. Again, I'm sorry for going through this so quickly, but electromagnetic disturbances and charges happen because the speed of light is finite and constant. These are deep, deep implications of the profound insights of Einstein and the special theory of relativity. And if you really want to know more about this, there's a book that explains it better than I can, and this is where I learned about a lot of this. If you ever read one physics book that I ever recommend, I've recommended this more than once, pick up this book. It is phenomenal. It's called Deep Down Things: The Breathtaking Beauty of Particle Physics by Bruce Sham. It is phenomenal. You will have a deeper appreciation of the beauty of the universe after reading this book. I guarantee it. But a lot of these implications in the last third of my presentation today were described eloquently in this book. And there's essentially no math in it. Occasionally a diagram or an equation, but almost all prosaic. So that's it for special relativity. Next time,
Wow.
I'll talk about the more general case of a space-time that is not flat, but curved.
Wow. Great. Thanks so much.
Thank you.
We'll see you in 2 weeks. I'll be talking a bit about the James Webb Telescope and some of the things that they're starting to do with it now that it's out at the
Lagrange point.
Lagrange point, I've heard it said, yeah.
Okay.
And a million miles away and ready to start doing our bidding.
Ooh, and the things that we'll uncover, hopefully.
Right.
Yeah. Thank you for tuning in. Thank you for watching. Again, questions or comments, I can't imagine you won't have questions after I rushed through a lot of that. Let me know. And stay safe and warm, and we'll see you soon.
All right.